All right, last time we finished up the derivation of the uncertainty principle, and on its own, there's not really a lot to that other than it was an exercise. I mean, that is a hard proof, although mostly algebra, right, or entirely algebra. It was still rather involved, convolved, multi-step derivation, so now you have that. Again, on your next homework, or maybe the next homework, I'm going to have you do some things with it. So you're not done with it yet. Those questions are a little bit harder than average, let's just put it that way. Okay, then we went to transformation of basis. And so I'm just going to repeat. Hopefully you can see that okay. It's okay?
Yeah.
All right, now I'm inserting a resolution of the identity. And I will write this in a, let me switch to gamma. I hate alphas and A's in the same thing. It can confuse you. And of course you know this to be the coefficient. Call this the coefficient of overlap, just the weight. Like how a sine function, remember you've seen this before, a sine function is 1/2 right wave, 1/2 left wave. Remember that from the first part of the course? So there you go. So that's your, I'm sorry, 1 over square root, that's 1 over square root of 2 for 1/2. Okay, all right, now we covered these unitary operators, and I think I'm just using this from the book, the subscript K. Seems like N was used before. So if you're going to switch basis from A to B, you just do this. And it's more important to know the transpose. And again, I can't emphasize enough, this is one of the few times you get to see what a transpose is. They're generally not that, they're usually defined as being no different than the operator, because most things are Hermitian. But for non-Hermitian operators, such as this operator, this unitary operator, this is the definition. And you can see how, again, these transposes act on bras. And just like a bra and a ket aren't, you remember how I said, oh, there's a one-to-one correspondence? That, that doesn't say anything, It's a bunch of words. I know the meaning of those words, but strung together like that, it's meaningless. It doesn't provide a clear path from one to the other, and because there isn't one. So that's awesome. So transposes are defined to work on bras. Again, that's a bunch of words with no meaning. It doesn't really tell you how to construct them. And again, you deal with them on a case-by-case basis. Generally, you don't have to deal with it because most things are Hermitian. All right. So anyway, so that's that guy. And then I covered how. Let's see. If we're going to switch to the B representation of state gamma, and so I should look at my notes from yesterday of the video. The video's up as well from last session. I think I used alpha instead of gamma, so I'm switching the letter here. Of course, that doesn't mean anything. So sorry. So I am. Let me just write all this down. Okay, so there you go. So now I've gone from a representation of, and this would be a column. This would be a column vector. This would be a matrix because this is only one element of a column vector. And so to turn a column vector to a column vector, you need a matrix. And I wrote that down last time, so I'm not going to rewrite it because it's really a pain to do that. Now, the magic, of course, is to recognize that the B representation is transformed from the A representation by the transpose operator. And that's why I was telling you that the transpose of the operator is actually the one that's easier easier to work with. Oh, sorry. Okay. So again, the transpose operator. It's easy to understand what this is, mostly because you already know what your starting basis is. This is the one you're trying to go to. So, like on your homework, I have you work with both of them. I give you ways to solve both of them. And as usual, the homework is a really good way. When you apply this to a real system, you really have to know how it works. So just do the homework, and as much as this is abstract, it'll be made very real. Then you should completely get it. Again, I always find this one intuitive, but this one is the one that's useful. Now, in terms of its utility, I switched your homework around because the way that, like in the book or in the class I took 20 years ago, it's easy to do this for spin systems. I mean, this is why you learn Dirac notation with spin, because, of all the things we can do, this is way easy. And so think about if I had started with plus and minus states, the basis states being Sx as opposed to Sz, it's not the same. It may be the same thing. It's simply wiping out every z and writing an x and vice versa. And there you go. And so that's kind of trivial. I'm not really sure about that. I think what you'd have to do is if I decided that X was my basis set, I think you'd have to run through that whole 2 weeks that we did of deriving everything to know what Z and Y would be. We did a lot of stuff to figure out what everything was, and you kind of would have to redo it all. So this transformation of basis, if you can figure out what your U and transpose operators are, then you don't have to go through all that rigmarole. You have to figure these out, but then that's it. Then you can change everything else. So that's why that would be useful. Now, why would you need to change Z to X? When would you ever run into that? The answer is really never. To some degree, this is an exercise in quantum mechanics, which is good for you because you learn to think quantum mechanically. But then again, like on the homework on the last question, there's a problem that is extraordinarily relevant. And I hope you can find it's actually quite useful. And maybe I'll try to do some more with that particular problem, the bonding between cadmium and selenium in the tetrahedral environment. It's very oddly specific, but still, though, it really teaches you a lot about sp3 bonding. Okay, so with that said, now you know how to turn Sx, the state, into another. Okay, awesome. But as you had seen as well, really operators. With operators, you actually know everything. Whatever is your world, your Hilbert space, and that would mean, in this case, spin up, spin down. Oh, it sounds like an electron. Oh, that's pretty important. Maybe it's a proton in NMR. Well, that's pretty important, right? Whole research groups are devoted to this stuff. You know that with the operators, that's actually really what you want, because you can actually figure out the states from the operators. You need the operators to define, you need the states to define the operators, but if somehow you have the operators, then you can define the states. It's a little bit of a chicken and egg. But it's, depending on which one you have, you want to be able to go forward from there. So that's why matrices are actually way more important. Okay, so let me put this in the A representation. Let's do the matrix. So we're going to switch to the representation of a matrix now. Again, the operator matrices are actually kind of more important than the states usually. Again, there's a one-to-one correspondence between them. One gives you the other, and vice versa. But if I had a choice between knowing the states or the operators, I'd rather know the operators, especially in matrix form. Okay. You know what? Let me actually start this way. Now we're going to assume that we know an operator in the A basis. Notice I've resolved an identity. There's the operator. do not get your M's and N's confused, because that would be very bad, because that would that means that you're not resolving an identity. Okay, so it turns out that this actually is relatively straightforward. Note that again, we're going to try to build a matrix. It's just going to be in a new basis. And so for any member, any entry, you know, I know that's one, I've drawn 1, 1 there, right? And then here would be 2, 2, and that's 2, 1, and that's 1, 2. So that's 2, 1, that's 2, 1, that's 1, 2. It's kind of, you know, I had a way of making sure that I'm self-consistent with how I define that. So anyway, so now I gotta build out the matrix for whatever operator this is in the B-rep. Okay, it turns out that if you recall, how did you ever build a matrix representation? You just simply made an evaluation with an inner product, right? So all of these elements are inner products, right? So recall that this is an inner product because this operator will let's operate on the ket. Again, that's always the easiest thing to do. We'll operate on the ket, which will spit out a number times and leave behind another ket, which then has an inner product with that. So that's why all of these are numbers, and numbers in quantum mechanics are always inner products. Okay, so this is how you built the matrix representation for all of these operators from the very beginning. I'm just going to put in, instead of just putting in this, I'm going to put in all of this in here. That's my trick. It's quite long and a little hideous. Okay, and now I'm looking at this thinking, oh God, where do I have room? Okay. All right, so I'm gonna write slightly smaller, and I'm gonna go kind of slow. Okay. Okay. Now recall that as long as this expression is, note that I'm actually only creating one element of the matrix, so that kind of sucks. All right. But at the same time, this hopefully isn't that hard to understand. You know, you've gotten used to this. Remember that this is really the matrix. This is just filler. Okay, A to the M operator. Okay, so this isn't so bad. Okay, so that's not so bad. Now what we got to do is now what we do now is do what we did before, and we're going to turn. We're going to transform. We know everything with A, so this I can't really deal with it. You know, learning how to deal with this is the point. But that means at this stage of the game, I can't have it there, not yet. I know everything about A. I know everything about A, so that's why I'm going to change B to A, because I'm okay with A at this point. And then when I know what my operators are, then I can deal with B, and then I'm done. Right, if you saw, you can see why I was saying I needed a little bit of, see why I needed quite a bit of space here. These get little heads, these are operators. You should have little heads, it doesn't matter, hopefully this isn't too painful to see. Okay, now.
That would be the transpose, right?
No. That means transpose.
Because it's split.
This ends up being to turn a bra into a ket. It only transposes operate on bras.
Okay, that's good.
Yeah. It's not fair. You really couldn't use with the regular operator because clearly I'm turning this bra into that bra.
Okay.
I'm actually kind of reverse engineering it actually, right? kind of basically what I'm doing. And then, of course, this operator is acting on a ket, so by definition, that is just the operator. Okay, now again, your act notation, it's a bit of a mouthful, but hopefully it's not that hard. Recall, though, that this is just like the 1-1 element. Oh, oh no. Now you got to build the rest of the matrix. Now, when you do this on your homework, of course, you can, you're just going to have like spin up, spin down, so it's actually not that bad, all right? But let me point out that the way that this is ultimately going to work is like this. All right, so look at that. Let me show you what the matrix actually looks like. And there's one thing that's kind of really funny about this, and I still to this day, I just derived it. I just derived everything. It's right in front of me. I get it. This is mostly just a lesson in algebra once you get used to the rules of direct notation. But now let me represent this in matrix form. Now note that, again, we are, I'll put it that way. I don't want to have to be writing stuff forever, all the A's and B's. So I'm just saying 1, 2, 2, 1 just to represent. And that's of course how you signify what your element is. Okay, and what is this? Let me drop here. Okay, plus 1 plus 2 plus 1 plus 2 dot dot dot. Then this is the operator that you had in the A basis. There's no, remember that, I know that because that's the whole problem is that I have this already, you assume you have it already, but for whatever reason, you have to transform it to the B basis. And then here is U itself. Let me just not do the hats. That's, although you all know I have a great affection for hats, so I'm not trying to be dismissive of my operators. But okay, let's not let that get in your field of view. I think that those are just attached. Okay, so now again, big picture here. To write this out in this form, I actually need to write, I would actually need to write 2 more sums for K and L. I just don't want to do that because it's already kind of big enough. So what I've done is I've taken this expression and I said, okay, now let's do all the matrix elements. Remember, this is the B rep. Instead of putting it in more direct form, I simply did those 2 extra summations of K and L. So these are K and L. And I'm just writing out the matrices instead of, yeah, it's just a little bit easier. And so in terms of operator notation, this is it. Okay. Now, the thing I was going to tell you that I find really bizarre is that you have a column matrix for a ket. You use an operator to turn it to a different column matrix. No matter how much you're if you're comfortable with matrix algebra, it's still something you learned in middle school. Okay. Yeah, I find it weird that you have to have 3 matrices for the operators. Like, okay, why not just this and that? Why not? I don't know. I just derived it, so it's not like it's impossible. It's from outer space, but I just look at it and I kind of bristle with it. I just don't know why I need 3 matrices as opposed to just 2. But there it is. Okay, and now also on your homework, you had so much of quantum. I really like to do quantum in the form of matrices. So that problem 5 that you have, that is actually something I'm working on right now for a paper, and I really like doing that. That's like atomistic quantum mechanics. I'm making bonds. I'm actually drawing wave functions, and I'm doing that with a matrix. So I'm like super happy about that. So I love doing quantum mechanics in the matrix form when I can get away with it. Some of the things you have to do on the first 2 or 3 questions is, they're a little esoteric, and these are just proofs for proof's sake, but again, there's value in that. And 2 of them, I should have mentioned this before. There's a couple of things on the review session I realize I haven't mentioned before, but let's do, and so watch that. But let me just very briefly point out, you can say E to a matrix. Now I remember when I was confronted with this problem, the same problem you have. I'm giving you the same problem I had when I was in grad school. We were all like flummoxed. Yours truly, being clever, thought, why not write out this matrix in Taylor form? Identity plus its squared plus 1/2 its squared plus 1/3 cubed. And I think that's actually correct. But it turns out, and so I was very proud of myself, it turns out one of my classmates looked it up or claimed to have known somehow that all you do is you just take the matrix and raise every element to the nth power. Yeah, it ends up being real. It's just like stupid easy. It's the easiest thing you could ever do. It looks like, oh my God, look, that's a mathematical idea. A PhD would know about. It's actually something a high school student can handle. All right, so there's that. Now there's also some concern about making sure that you don't change the nature of the problem by these basis transformations. You can't fundamentally change the operators because that changes reality itself. Right? If something's spin up in the z direction, that's all fine and good. It's still going to be that way whether you choose to do the problem in the z or x or y basis set. So there's an idea that you can change these matrices, but you can't change the eigenvalues or eigenstates of these matrices. Or the spin of an electron is no longer 1/2, right? And that's, no, you're not allowed to do that. So some of the things are, I don't recall this one. I may be misquoting this, so let me just say it, but I may have to come back on this. One is that I think the eigenvalues of a matrix, which is an operator, so I'm talking about the eigenvalues of the operator, don't change when you do these transformations. So there's that. So what I can do on the next homework set, take the last problem where you're working the SP3 basis set, and spit out the eigenvalues. And they're actually the same. I've already done it. Now, for that to be true, the determinant of the matrix doesn't change after one of these. This is called a unitary transformation. And that just means you change basis. Okay, another thing is, I forgot why this is important, but the trace doesn't change. That's also hideously important if you are a mathematician of matrices, and there are mathematicians of matrices. When the trace of a matrix of 2 matrices are the same, then that's like one of the most important things that you could ever know about whatever your mathematics is. Okay, now you have to do a bunch of these. This is really similar to a problem, the answer to one of the problems you're dealing with right now. Now, a trace is the sum of diagonal elements, and maybe you have to stare at that for a second to realize that's what I've written. That is the diagonal. You know it's the diagonal because it's the same little dash on both sides. Okay, now what I'm going to do is resolve the identity twice. Because what I'm doing is I'm changing basis. And of course, resolving identities, you slip it inside. Well, sorry. It's hard to know where a resolved identity fits. You don't have to slip it inside. I mean, you see where I tucked it in. I guess it can kind of go anywhere, but of course it goes where you answer the problem the fastest. That's where it belongs. Okay. Now, this is, again, one, I'm going to do something with this that is how you answer one of your questions, just heads up. And I'm not trying to be quiet, I don't quite remember which one, but anyway, it's been a while since I looked at it. Okay, so what you can do is you can rearrange these. I don't need to rearrange the sum. That, I don't think that actually means anything. Okay, I am going to, I'm just looking at my notes. Okay, I'm going to keep this one. All right, so that one's there. Then what I'm going to do, okay, I'm going to then write this one. Now remember, these are numbers. Oh, I see why I'm doing this. Actually, I forgot why I was doing this a second ago. These are inner products. They're just numbers. 5 times 4 times 3 is 3 times 4 times 5. That's fine. But you may notice that I did something clever. It just resolved an identity. Right? So now, get rid of it. What does that do? Let's see. Now I've got, this hasn't changed. Okay, so you see the trick here is now I brought this and that together. And of course we're assuming, you know, if I put all these B dashes, B1, 2, 3, 4, 5 together, they're the functions, they're the eigenfunctions of an operator. They're a basis set. They're all the particle in the box states. The A's are the harmonic oscillator states. They span the same Hilbert space, S. Anyway, that's a delta, that's a Kronecker delta function, right? Remember, this is the overlap of two states, and we're assuming everything's Hermitian. The unitary operators are not Hermitian, so that's a little funky, but it's safe to assume everything else is. So therefore, I'm assuming that I can, it's 99.99% of the time, it's absolutely safe to assume that these states are just Kronecker delta functions. And remember what that does is now you can legally wipe out one of the sums and turn all the double dashes to dashes, or vice versa, just be consistent. And I'm sure that there's some rule that you pick the left or right one. It literally doesn't matter. I like single dashes better than double dashes, so I'll get rid of the double dash. I'll get rid of the double dash. So everywhere I see a double dash, I write a single dash. In case you get a little flummoxed on what to do with these Kronecker deltas. Okay, so the trace in the A rep and the trace in the B rep are identical. So that's all I've done. And also I've given you this, again, this is pretty much how you solve one of those problems. And it's just a little, something we could do just because we can do it. Last bit, and I'll have you do a little bit more with this on your homework. I've already introduced you to the fact that you can get eigenvalues from matrices. And I forgot what problems I had you do, but I showed you what a eigenvalue of a matrix was, and then you did some MATLAB. So let me point out that if you plug in, let's see, let's do S. See, now, you can see why, this is why I really want operators. I don't, if I have the basis states, that's fine too, but I'd rather have the operators. Operators give you everything, especially Hamiltonians, so they're very valuable. Okay, so let's do SC. So I am describing Hilbert space for a problem I have, and this is, and somehow the great turkey in the sky swoops down and gives me this information. Thank you, great turkey. Now I know absolutely everything. I have all the answers to my problems. So I asked the great turkey about an electron that's spin up or spin down. This is what the turkey told me. And I know the eigenvalues, right? So now in this case, the matrix is diagonal. So I don't need MATLAB to do it. I can do it symbolically. I can do it numerically. I can plug this into MATLAB, and I can say Eig of this matrix, and MATLAB will spit out h bar over 2 minus h bar over 2. And hopefully you recall how to do that. What you do is you, oh god, how did I put this? Let me see how I did it in my, well, let me make sure I did. This is from your book. I want to make sure I'm not completely. Well, yeah, let's just do this. Okay, here we go. Here we go. Here's a good way to do this. Okay, the operator times its basis state gives the eigenvalue times its basis state. Right, so on the S spin up, it would give me the plus eigenvalue, which is h bar over 2. The state comes back. If it was the minus state, then it would be minus h bar over 2. That's what I mean by lambda plus minus. Okay, now in matrix form, and I'm just repeating what I did before. Let's just do a single state. We'll do a single state. You have this, right? So do you remember? Do you remember this, or do you want me to rederive it? You're okay? You want to see? You want to see me rederive it? All right. Okay. Let's see. All right. So you have to pick a state, by the way. So at this point, so I'm bringing this over. So I subtracted this from there, and then I factored. That's not a I just wrote down the same damn thing, didn't I? Yeah. So we'll pick one. This is shorthand, right? That's shorthand for two equations. So I have to pick one. Now what I do is I factor. So where that probably got confusing was that you have to remember that this is really, you can't do this. You have to have it as an identity matrix. Okay, so that's where that comes from. Now, remember that for reasons that actually I don't know about it, I'm sure I could understand it if I Googled it. For this to have a solution other than 0 equals 0, remember when you're trying to solve back in middle school, a plus b is 1, a minus b is 2. What's a and b? And you do that with, that's when you learn matrices, right? You can solve that with matrices. But you learn that you could always do 0 equals 0. There was always the trivial solution was always going to show up, and of course you always reject it. Okay, for a non-trivial solution, oh wait, no, is that? No, is 0. Sorry. Whoa. Yeah, that was absolutely wrong. All right, for a non-trivial solution to exist, the determinant of this must be 0. And if you can do that, then you can work with this beyond saying nothing is equal to nothing, which is not useful. It is true that nothing is equal to nothing, but that doesn't advance anything. So, and again, we've done this. I don't quite know why that is. I haven't really bothered to look that up, but regardless. Okay, so tell you what, let's, now this example is stupid. I think this is the one I gave you, right, on the homework? I think it was this one. It's stupid because the matrix is diagonal. And so, tell you what, let's do SY. Okay, so let's do that. And H bar over 2. And let's do, for the, I'm going to do this for the, SY. No, sorry. No, I'm getting the eigenvalues. I'm getting the eigenvalues first, right? Okay, so I'm just figuring out the eigenvalues. I need to worry about. No, I screwed this up. It's for both states. Sorry, I'm jumping ahead of time. This is how you get all the eigenvalues. I wrote plus and minus because I already know there's only 2 of them. Sorry about that. Now, why was I flummoxing so badly? You'll see in a minute. So let me just do this problem. Sorry about that. Hopefully your minds aren't ruined for life. Again, let's know what a identity matrix is. Okay, and then this ends up being minus lambda. Okay. Now, the determinant of this, of course, is that diagonal minus that diagonal. I have no idea why. Now, anybody ever thought of this stuff? Oh, that's plus. Minus lambda, plus lambda squared. Then the diagonal, see, I'm going to have minus the other ones. So that's minus plus II minus. That's, I know, real pain in the ass to keep track of. Okay, then, again, set it equal to 0. And look at that. Okay. So this is just a walk down memory lane. That you've done this before. You even took all the same steps. Another interesting thing is that it's like the book mentions this. Sx, Sy, Sz, they can all be derived from each other using unitary transformations. Again, you're figuring some of that out on your homework. And because of that, they have to have the same eigenvalues. And that's why one of the questions is to show that the determinant doesn't change. So they all have the same eigenvalues, plus or minus h bar over 2. All right. Now again, I hope you don't look at this as like, oh, I haven't seen this before. No. This was on one of your homeworks. All of this was on a homework before. This is the thing. I don't think I had you do this. Now there's the next step. Now you're going to see why I got a little flummoxing here. Now you can figure out the eigenvalues. So when it comes to this, eigen that of matrices, it's a 2-step. Figure out the eigenvalues first, and then you can figure out the eigenfunctions after. Figuring out the eigenfunctions, it's a little bit difficult. Now let's hear from MATLAB. MATLAB does it for you. Cool, but you should know how it works. All right, and this is where you have to pick one. So that's why I was mixing 2 subjects together at once. And they're not, because they come in steps. So let's do lambda plus. So we're going to solve the lambda plus state. Okay, so let's write the operator. So I'm writing the SY operator. Now here's the thing. I'm looking for the eigenfunction. And I'm just writing the eigenvalue equation. Now it turns out that now that I know the eigenvalue, so the crazy thing about quantum, remember I mentioned this a long time ago. You have a Hamiltonian, but you don't know the wave functions or the eigenvalues or the energies. How the hell do you solve that? Well, you do it this way. Kind of amazing what mathematicians come up with. You have one equation and 2 unknowns. What the hell? But you can solve it, right? So we've already talked about using the eigenvalues. Okay, okay, the H bar operators are gone, those cancel, so life is actually kind of easy. Okay, 0A minus IG, IA. Okay, column matrix is equal to column matrix, and therefore A is equal to minus IB, IA is equal to B. Okay, now you do have a chicken or egg problem, and in fact, one equation with two unknowns is in fact insolvable. So that actually did not go away. So you need another equation, and guess what? You do have one. A squared plus B squared is 1, that's normalization. The state has to be normalized. All right, so now you have two equations. Okay, so let's do A squared. A squared is A squared. But B squared is IA squared. And that better be equal 1. And, okay, the absolute value of A squared, of IA squared, is still A squared. So I got 2A squared is equal to 1, and therefore A is 1 over the square root of 2. And then B is I over the square root of 2. And therefore the SY plus state is just as I had done before, 1I. Which, if you may also recall, is this, if you're a little bit more comfortable with this at this point, you know, whichever representation you're more comfortable with, there you go. Okay, so again, I just want to point out that how powerful it is to have these matrices, to have them in different bases, a little bit about mathematics of matrices, a little bit about how eigenfunctions work. Again, thank MATLAB. MATLAB will just do this for you. I'll throw some problems at you on the next problem set using that SP3 basis set, because that's very, that's a very real thing, right? And after that, okay, so next time, we'll have your homework, I promise. Next time we are going to massively switch directions. We're now done, aside from your homework, we're now done with spin up, spin down. There's literally nothing else we can do. We're actually going to go back into the world of ETIJX.